So we're slowing up. So what I'm going to do, and the participants coming in as people are introducing themselves, I'll introduce myself. I'm David Layzell. I'm the Energy Systems Architect with the Transition Accelerator, and also a strong supporter of the Edmonton Regional Hydrogen Hub, the organization that brings you this webinar today. Before we begin, I'd like to acknowledge that the Edmonton Regional Hydrogen Hub is located on Treaty 6 territory. It's a traditional meeting grounds and gathering space and traveling route for the Cree, the Sooty, the Blackfoot, the Métis, the Dene, and the Nakota Sioux peoples. And we encourage everyone on the call today to consider and reflect on the territory and the treaties and the people where you live and work, and the peoples that have lived here for thousands of years. This webinar is part of the Edmonton Hydrogen Hub's webinar series on building a low-carbon hydrogen economy in the Edmonton region. These monthly conversations are meant to provide industry, government, and investors with the knowledge and tools that they need to take advantage of Edmonton's regional potential for low-cost, low-carbon hydrogen production and to contribute to the development of a new energy system that uses hydrogen not only as an industrial feedstock, but as an energy carrier itself, and as a possible export product for export markets. Now, you can see from our webinars on the website at erh2.ca that this presentation will be available there tomorrow. So we'll have this presentation up there tomorrow. And if you find it interesting, we encourage you to share it with your colleagues. For information and updates about future webinars, be sure to join the ERH2 mailing list and follow the ERH2 on Twitter and LinkedIn. And Ashley, maybe if you could put into the chat box actually a link to the newsletter, that would be greatly appreciated. Today's topic is pipelines versus power lines, the economics of energy distribution. Now, in Canada, the distributed combustion of 4 energy carriers, gasoline, diesel, jet fuel, and natural gas, account for 45% of all greenhouse gas emissions in this country, and another 25% of national emissions associated with the recovery and reforming and refining of the oil and gas that makes these energy carriers. Therefore, it is pretty clear that if we're going to address climate change, we need to replace the consumption of these energy carriers with zero emission energy carriers like electricity or hydrogen that when they're being consumed, they don't produce any emissions, and we have to be able to produce those energy carriers with minimal or no emissions as well. Now, most visions for net zero emission energy futures have major roles for both electricity and hydrogen, but these energy carriers cannot be produced precisely when and where they are needed. And just as population density and energy demand varies widely across Canada, so does the regional capacity to produce, use, and store these energy carriers. Clearly, we need to connect supply to demand, and the predominant technologies to do so are pipes and wires. The cost and reliability of energy transport and storage infrastructure is a crucial issue within the energy industry, and has implications for energy access, affordability, the environment, and public safety. We're going to hear today about a project that was funded by the Australian Pipeline and Gas Association entitled Pipelines versus Power Lines, the Economics of Energy Distribution. This work was done by Australia's GPA Engineering, and they analyzed the cost of energy transport and storage across a wide range of different gases and electricity infrastructure options. And we're going to be hearing more about that today. I'm going to introduce the two speakers today. Josh Wickham. Wickham is a technical lead engineer and a passionate pipeliner, and I think pipeliner doesn't come up in my dictionary. I think it's a good Australian word. And is the industry manager for pipelines and compression at GPA Engineering. Over the past 4 years, he has led projects in hydrogen production and facility design that are now in operation. He's also worked in a number of other projects, including ones to implement hydrogen blends and conversion to 100% hydrogen into existing gas systems. Josh is also the lead author of the Hydrogen Pipeline Code of Practice under the Future Fuels Cooperative Research Centre in Australia. They develop rules and guidance for new and existing pipelines for hydrogen service. I'd also like to introduce Jordan McCollum. He's the National Policy Manager at the Australian Pipelines and Gas Association, where he works on energy policy. He has a career in gas industry. He's a career gas industry professional. He's experienced in the commercial and operational innovation management of technically complex energy value chains. And he represents, of course, the organization that supported this work. I'd like to pass it over to you now, Josh. And thank you very much for joining us today. To the audience, please, if you have questions, put your hand, no, don't put your hand up. Put your question in the question and answer box, and we'll get to it at the end of the presentation. Thank you. Over to you, Josh.
Thank you, David, for that introduction, and everyone for joining us today. As David mentioned, GPA Engineering were engaged by the Australian Gas and Pipelines Association to look at a study comparing the economics of energy transmission and related storage as well. So we're engaged to look at the economics of transporting energy. It's focused really on the transport element, and also assess other factors like reliability in that question around, how we transition to a low carbon future. What sort of infrastructure is going to be the highest value for us as an industry and as a country, and looking at the various differences between electrical transmission, so HVAC and HVDC, versus moving energy using gaseous molecules like natural gas, which is what we do currently, and hydrogen. I'll pass to Jordan McCollum from APGA, who engaged us for this work, to give a bit more background of why they initiated this activity, and then I'll jump through our presentation and go through a lot of detail around the study methodology and other aspects of the work that we executed. Thank you, Jordan.
Thank you very much, Josh, and thank you all for the opportunity to have a bit of a chat to you today. So the Australia Pipelines and Gas Association, we represent the owners and operators of gas pipeline infrastructure in Australia, as well as a lot of the industry that feeds into helping that industry thrive. In the policy space, we're focused on two primary fields of interest. The first being ensuring that nothing changes to prevent our existing infrastructure from providing low-cost, high-utility energy transport and storage today. But the second piece of that puzzle is that we are at the forefront in Australia of helping to develop what we refer to as a renewable gases industry in Australia, such that renewable gases like hydrogen and biomethane can develop into the existing gas industry, much like solar and wind is developing into the existing electricity industry, to decarbonise those simultaneous or parallel renewable energy pathways and renewable electricity and renewable gas. Now, when we were talking about hydrogen and the possibility of hydrogen pipelines, there are a lot of little questions or challenges that would come up, and they'll be framed as absolute showstoppers, game over for the potential hydrogen pipeline industry. Things like the embrittlement conversation, things like the heating value conversation, etc., were all kind of framed as, no, it can't happen because of this. That didn't really make a whole lot of sense to us, because we knew that hydrogen pipelines could be built. And we also knew that, economically speaking, gas pipelines were already providing lower cost energy transport and storage for energy customers in Australia today. And it made sense that the hydrogen pipeline industry would follow. However, when we looked for publicly available data, we couldn't actually find a whole lot of like-for-like data. And that data which was out there was definitely not in an Australian context. So we approached GPA Engineering to undertake like-for-like techno-economic analysis between HVAC and HVDC power lines, as well as hydrogen pipelines and natural gas pipelines, so we can understand the relative techno-economic differences between those different pathways. And I won't spoil the surprise at the end from Josh's presentation, but the industry, what the industry saw through the study was pretty well as expected. But yeah, so that's really what led to the study, and The one thing that was brought up just before we started, it is worth noting that the study does focus on just the transmission pathway, and that was really to create the building block for broader techno-economic or supply chain analysis. So we did have a focus just on the transport infrastructure, not on the production or the utilization, so that when someone's considering that supply chain, we wanted them to be able to pick up this data and put it between a supply and a demand case and build out that supply chain comparison effectively. So that's about it from me. I'll hand back to Josh, and in the Q&A, feel free to pass any questions through that you may have.
Thank you, Jordan. So just as a brief agenda, I guess we've gone through the intro and study background. I'll move into a bit of an Australian context. I recognise that all of our audience today is primarily from Canada. So we'll talk a little bit around the energy transmission context within Australia. A slide really around hydrogen and why that's been looked at within the Australian industry, electrification, and what the the discussions that are happening in policymakers in the media around electrification. And then I'll step through the study methodology, the outcomes. So outcomes associated with looking at reliability assessment in terms of loss of supply scenarios, transmission costs in the form of levelized costs, as well as energy storage associated with pipelines, so via line pack, via storage within the actual asset, or other options to increase energy storage like looping, parallel lines. And from the electrical side, that's looking at really BESS systems and pumped hydro were the two types of electrical energy storage areas that we looked at. And then step through some key takeaways, some final thoughts, and then we'll have some time, I think quite a bit of time for questions at the end. So in terms of the context of existing pipeline infrastructure, what you can see on this screen on the right-hand side is, I guess, the major oil and gas deposits within Australia. There's a large one in Central Australia, covers 4 different states. We have quite a few offshore basins as well. All of our major users of energy are pretty much confined to major regional towns and the capital cities, which are on the coast. So we're moving a lot of energy from existing oil and gas reserves, which are quite centrally located across major spine lines, these long transmission pipelines, to concentrated populations in our capital cities, where it also has most of our major industrial consumption of gas. On the left-hand side, you can see electrical transmission network. This is from 11 kV all the way up to 500 kV overhead and underground power lines. They're crisscrossing most of the heavily populated areas of Australia. So there's lots of areas of this country which are unpopulated, certainly by concentrated populations where we don't have a lot of energy infrastructure. And that sort of has had an influence in the design of our energy infrastructure system, including our pipeline system. As a result of that, pipelines within Australia, and they are designed under our own standard, as AS285, basically an equivalent to the Canadian CSA Z662. And they're typically moving gas over very long distances, generally around 200 to 500 mils diameter, so smaller than what you often see in North America. We do have some large-scale pipelines have been developed really for moving coal seam gas for LNG export, but for the most part, it's long distance, smaller diameter, high design pressure, and high stress pipelines that move gas across Australia. So it's generally between 7 to 15 MPa. Constructed using high strength carbon steels. And like I said, operating under high stress, 72, that's about 80% SMIS. There is some differences when it comes to hydrogen transmission. So I guess the study used, current design parameters for hydrogen transmission. We did still cap the pressure to 12 MPa, and the stress to 50% SMYS. So it's a more conservative design envelope at the moment until more research is underway to push that boundary towards high stress limits that we're used to under ASTI 5 for natural gas service. I've got some typical examples of Australian transmission line assets. We do have some long transmission lines of various power loads, and we're seeing, I guess, a lot of investment in new high voltage power line infrastructure for Australia, and quite a few announcements around really expanding our electrical infrastructure grid to really support greater uptake of renewable developments in Australia and moving electricity. Like Jordan mentioned earlier, we haven't had a very mature debate around different forms of moving energy. There's been a lot of discussion around the electrical version and electrical transmission infrastructure, which is sort of part of the reason why this study was of really high value. On the left side here, we've got I guess an overlay of Australia on the map of Canada. So if we look at the overall scale of both countries, we've got a sort of similar sort of size, and that does result in some similarities around how we're moving energy between our two countries. From I guess a gas production, gas transmission, distribution, Australia is a smaller nation in terms of how we produce and consume energy. We are a big exporter, but this is hopefully giving you a bit of an idea of some of the relativity decisions between how you interpret the data that's presented in this report and what scalability that is to your situation in Canada. I won't talk further on this one, but I was interested in looking at the Canadian gas pipeline map shown on the left, and how that compares with the Australian one, which I showed over here on a more rudimentary map. So hydrogen, like for Australia, it's been really a big focus from the federal government, really supported by a chief scientist a few years ago, to look at hydrogen as a real potential pathway for decarbonisation, not just our domestic energy needs in Australia, but really our export of energy in Australia has been a really large part of our trade economy, and we have been supplying energy to energy poor nations for many decades, particularly countries like Japan and Korea, our close neighbours. That's principally been in the form of coal and LNG. So as a country, we've got the luxury of a lot of open space, a lot of solar potential across Australia, a lot of really good wind resources, and often in locations around coastal areas of Australia, some good coincident wind and solar resources. So we're really looking at hydrogen as an ability for Australia to ship our sunlight or ship our renewable resource overseas to Japan, Korea, China, and other energy poor nations. Hydrogen's a really good form for us to move that energy. So that's really why we're focused very heavily on a domestic, an export sector, but we're also looking at hydrogen for decarbonising our domestic gas sector, effectively transitioning from natural gas to hydrogen in many areas where electrification isn't the most cost-effective outcome. So I guess under that context, there's been a lot of investment in sort of small scale domestic hydrogen projects, including blending hydrogen to natural gas distribution mains for providing blended gases, some trial projects. That's now really going through feasibility for large scale hydrogen export projects. And a lot of those big export projects are moving energy often around 100 to 200 kilometres from a really good renewable resource to an export port at the coast. And a number of those projects have been looking at this question around how do we move energy most efficiently for these projects, driven by a renewable energy resource, convert to hydrogen via electrolysis. So we're looking at green hydrogen. Do we move that energy via power lines, via electricity, and have hydrogen production and ammonia synthesis or other carriers on the coast? Or do we look at pipeline infrastructure to move that energy? So this question isn't just one for us interested from an industry body group in Australia or more broadly, but it also has been coming up from time to time in some of these export projects. I guess the hydrogen sector in Australia as well also has drawn a lot of support and co-funding from federal and state governments. So it's very much has a lot of momentum behind it in Australia. It's certainly recognised as real. It is happening, given the work that's going on domestically as well as internationally. So with that support, with some of that natural advantage, with our, I guess, a long history of supplying, reliable energy via natural gas, it may come as a surprise that there's a lot of discussion focused on electrification, and that has been really happening a lot in Australia. And what we're seeing, I guess, in sometimes in policymakers, often in media, from some sources, is a not very clear or a fully realised debate based on data. So that was really, again, one of the reasons why this study was initiated, was to provide a bit more information to the public sphere so that policymakers, the public and the media to some extent can help to understand this more complex energy equation that we have, and sort of move away from very, I guess, potentially biased thinking or potentially sort of single solution thinking. And I guess in our experience for the energy sector and how it's interconnected, we really needed better comparative information. So we have more advanced system understanding of energy transmission and associated storage. We wanted to really inform policy decision making on energy infrastructure through the transition to net zero. Internationally, we're going through this big energy transition. We're still somewhat at the early phase of that. So there's a lot of work to go through and a lot of thinking that needs to happen now around how we make the right decisions for investment and for policy. And we wanted to promote a more mature debate of energy transmission infrastructure. And like I said earlier, improve our understanding, support data-driven overall system consideration, and remove uncertainty from the transmission element, which is what we're focused on in this piece of work. So the work itself involved developing a sort of 250 number case map that was developed to assess this comparative cost in moving and storing energy over distance with different medians and different scales. So we looked at transmission carriers using gaseous fluids, so natural gas and hydrogen gas separately, as well as electrical infrastructure, high voltage AC, and high voltage DC. We looked at a range of distances from 25 kilometres up to 500 kilometres, and a range of capacities from 10 terajoules a day up to 500 terajoules a day. So these were sort of representative of what we thought matched well with our current pipeline infrastructure and what may be required in the future as we're moving different fluids as well. And then we looked at the question of storage, and storage is becoming increasingly important in Australia in our energy system, particularly as we're slowly, sometimes chaotically, moving coal-fired power generation off of our, out of our energy generation mix. We're seeing a much more increased uptake in renewable energy as providing a large proportion of our energy that's very variable and dependent on weather, particularly for wind and sun, which is a large proportion of our renewable energy potential. So really the question of energy storage is becoming more critical to complement that variable generation supply. So we looked at storage capacity of 0 hours and 4, 12 and 24 hours, recognising that need for storage as being really important in the future energy mix. Important thing as well, we focus on new assets rather than repurposing. So we wanted a very, I guess, uncomplicated result. We're looking at new assets, new investments. Repurposing is being looked at quite a lot in Australia and in the pipeline industry around how can we repurpose existing natural gas infrastructure for hydrogen service. We might talk a little bit about that in questions. So as Jordan mentioned, the focus on this study really was on the transmission elements. You can see that in blue. This is the hydrogen overall supply chain example. In blue is really the focus of what this study was looking at. So we're excluding upstream processing or compression, excluding downstream conversion efficiencies to one form of energy or another. We're assuming the pipeline assets are buried. That's represents the vast majority of pipelines across Australia. It is more costly than above ground, but it's effectively expected by the community in Australia that they're buried pipelines that run through public land. HVAC and HVDC assets have assumed to be above ground. That is the cheapest cost approach. There is perhaps also a public good or visual amenity reason to go for a buried electrical infrastructure, but for the most part in Australia, a lot of that has been above ground for major transmission lines. For buried assets, we're looking at probably somewhere between 2 to 10 times costs more expensive for HVAC and HVDC, so we thought we'd use the more cheapest cost approach in this analysis. Pipeline storage, like I mentioned earlier, is based on line pack, increasing the diameter, so oversizing the pipeline or looping, doubling the asset or tripling or having multiple parallel pipelines for a given fixed distance. And electrical storage is based on battery energy storage systems, so BESS, and pumped hydro energy storage system. And these were really the most mature and adopted technologies. There is more development in different types of electrical energy storage. That's not quite commercially viable yet, so we focused on what was mature technology of the day. So this slide also just again represents the focus of our analysis is on the blue items in these energy equations, so the transmission aspects and the related storage associated with those transmission aspects. So moving on to study outcomes. So one of the important pieces of our work was really looking at a reliability analysis. We didn't want to focus solely on the economic case looking at transmission. So recognizing that energy security of supply is something that's very critical within the public in Australia, and what they expect to have available when they go about their business. So this includes both major industrial companies all the way down to individual homeowners. People expect energy to be available to them, and supply can be quite disruptive. So we thought, let's look at the differences between reliability and loss of supply scenarios against the two types of infrastructure. So on the top left-hand graph here is a rate of Australian incident events. This is in gas pipeline infrastructure on a per 1,000 kilometres per year basis. It has been trending down, which is a good thing. These represent just incidents in general, not loss of supply scenarios. So on the top right-hand side, the two pie charts, is some further information in how we got to a loss of supply scenario. So the first one in the middle is really for information to understand where our pipeline assets, what is the cause of an incident. External interference for us is still the largest cause of incidents for Australia's pipeline infrastructure. Corrosion second, then erosion, construction defects, lightning is becoming more prevalent. And then the top right hand side is the severity of incidents. So a lot of these incidents are sort of corrosion, no leak, gouge, some deformation, coating damage, not resulting in a loss of supply scenario that may result in an inspection, some action for the pipeline operator, but not necessarily a shutdown. The remaining sort of 14% on average over this period is associated with a leak scenario or a rupture scenario. So we've classified both of those scenarios as loss of supply. In terms of a leak scenario, that can be a reduced pressure, supply remains. But in order to do the assessment, we're assuming that sort of 14% of these overall incidences is a loss of supply scenario. Bottom left-hand graph is the equivalent for high voltage electrical network reliability. So these are loss of supply events for electrical transmission. Again, it's been trending down, but there still is quite a substantial difference between these events for pipeline infrastructure versus power line infrastructure. A few reasons behind this. Again, I mentioned earlier around a lot of our power line infrastructure is above ground. It is exposed to the weather, exposed to bushfires in Australia and extreme weather events. All of our transmission gas pipelines are buried, so they're somewhat more protected to the environmental impacts and weather events. And certainly what we're experiencing in Australia is an increase in these scenarios. So I would probably expect over time, as we move forward into realising the outcomes of climate change, is that we're going to see more extreme weather events. So above ground infrastructure is going to be more vulnerable to that. There's some images here of major tower lines that have been toppled or damaged. That's from a statewide blackout event that occurred in South Australia, my home state in Australia. There was an extreme weather event, a couple of tornadoes, which is quite rare in South Australia. And it resulted in 3 major transmission overhead power lines being damaged and disconnected from the network. The resultant, disruption to the energy grid initiated some shutdown sequences of a lot of wind turbines, which we had very high penetration of wind on that day. And there was a series of scenarios that led to a statewide blackout. So there was a lot of big learnings from that for South Australia, for the Australian government around the energy system and how we can make sure we avoid these sort of loss of supply events. But it's just an interesting one that the vulnerability of our systems to weather events is quite different between these types of infrastructure. Fortunately, in Australia, we haven't had many pipeline rupture scenarios. We have, a few years ago, a lateral did fail and that disrupted supply to a regional town. But for the most part, we've been quite fortunate that most of our pipeline operators are managing their assets quite well and avoiding incidents in service. So taking that information, we converted that to just a simple table that looked at events per annum per 1,000 kilometres installed. So we can get something that's a bit relative across these 2 pieces of infrastructure. Looked at a period of 9 years where we had data for both transmission pipelines and HP power lines. And we can see there the approximate length of those assets across Australia, quite comparable. The number of loss of supply events per annum, and then events per annum per 1,000 kilometres installed. And there's quite a substantial difference. So there is an order of magnitude difference between reliability in terms of loss of supply for these 2. And so really a key outcome for us was that gas transmission infrastructure is more reliable with an order of magnitude less loss of supply events per 1,000 kilometres per year across the past decade. And like I mentioned, overhead power lines are more susceptible to weather events and natural disasters. So that's one of the reasons why we do see this difference. I'll step back into the actual study work looking at getting to a cost comparison, a levelized cost comparison. So this case map you see here is looking at the results of the pipeline sizing that we did for natural gas, one of our fluids, for 25 kilometres, 100 kilometres, 250 and 500 kilometres, those 4 quadrants across the page. The results here show the various pipeline diameters required for each of the 4 size scenarios, as well as looking at different storage scenarios. So from the left-hand side of each quadrant, we're looking at zero storage in pink, is 4-hour storage, greens 12, purples 24 hours. So we're seeing obviously the size of the pipeline required is larger. And once we get to the high storage cases, we're looking at multiple parallel pipelines, particularly for the short pipeline scenario, 25 kilometers. The longer pipelines we have, there's more we can accommodate within the actual transmission asset without needing to oversize as much or loop as much, because we've got more distance to play with. I'll show you the next slide, which is the equivalent for hydrogen. And an interesting thing between the two is for the zero storage transmission scenarios, there's not too much of an increase required for hydrogen infrastructure cost. So transmission can be relatively equivalent. Once we start looking at storage, then the energy density reality of hydrogen starts to come into play, and means that there's more asset investment required to get an equivalent energy storage than we're looking at for natural gas. So you can sort of see that in this page. We're requiring larger diameters, more parallel pipelines in order to accommodate that amount of energy storage for each of these scenarios. So I'll just flick between the two so you can perhaps see some of that difference. So onto the results. So this is the transmission cost comparison as a levelized energy cost in dollars per gigajoule over distance. So the chart in the left-hand side of your screen is showing over the distances, what is the change in our levelized cost against these 4 types of energy infrastructure options. So in blue, we've got our natural gas pipelines. In green-blue, I guess, is hydrogen pipelines. And then above that, HVAC power line, then HVDC power line. So this example where we're looking at on this graph on the left-hand side is for the 50 terajoules a day scenario, equivalent to 580 megawatts of energy, and zero storage. And so what we can see with these results is somewhat as expected. The gas pipeline levelized cost is by far the cheapest. That difference in costs is improved over distance. So the longer the distance is to move energy, the more cost effective natural gas is. Natural gas pipeline infrastructure is at moving energy more cheaply. Above that is hydrogen. So hydrogen is more expensive for the reasons I mentioned in that previous slide. There still is quite a large gap before we get to our HVAC case, and HVDC is generally above that again, except for a couple of scenarios. On the right-hand side, there's a few other graphs of our results, looking at the boundaries of the levelized cost assessment. So, top left, we're looking at 10 terajoules a day, zero storage, up to 500 terajoules a day, zero storage. And the bottom is you're looking at the same with some, but looking at distance as a scenario. So there still is, again, quite a gap between pipeline infrastructure versus our electrical infrastructure. So that's a meaningful outcome of the study, is that gap. When it comes to storage, we looked at 4 to 24 hours of storage scenarios. So 3 different cases, 4, 12, and 24, in addition to just the plain transmission case. The value, again, becomes quite obvious around gaseous compressible fluids in a pipeline and what that brings for you in terms of relatively cost-effective storage versus what you would need to couple with a HVAC or HVDC system to get an equivalent type of energy storage, and that's using BESS and pumped hydro. There's a larger gap between, really because of the difference in energy storage density for hydrogen as a molecule. But there is still quite a gap before we get to our electrical storage systems. So it's really saw that play out quite convincingly. It's a really important feature of our energy infrastructure is storage. So it needs to be really, really well considered when we're looking at policy and decision making around energy infrastructure in general. So this is a case where we try to highlight for a scenario what this could look like for an outcome where hydrogen has been supplied to an energy customer. Like I said earlier, a lot of the investments in Australia is looking at hydrogen as an export commodity. So we thought, let's look at this scenario where hydrogen is the end use. In the grey box in the middle is really, that's the economic analysis associated with our study. So the electrical storage and transmission, or the pipeline storage and transmission. So the bottom is looking at a 50% renewable energy supply. So some variability of supply with that. That drives a requirement for storage. So we're looking at 12 hours of storage to meet that capacity factor. This scenario, we chose 100 kilometers as the distance, and a 50 terajoules per day energy demand. And so we estimated, using some other rules of thumb and some costs conversions and efficiency conversions, if we're supplying, starting with electrical infrastructure as a starting point, what would the outcome would be for hydrogen? And we're still seeing quite a gap between customer costs at the end in the form of hydrogen being the product at the end. So $17.70 per gigajoule for using pipeline infrastructure versus $23.9 for electrical transmission infrastructure. So I've had some discussions with Jordan and APJ about this work. Obviously, what we need as an overall energy map is to really understand the efficiencies and also other end use scenarios. So there's going to be scenarios where hydrogen isn't just produced for direct use in some of infrastructure or direct export, but hydrogen is going to be converted again to electricity, where hydrogen is used as a storage to support the electricity system. So as part of, I guess, wider system modeling, then that's certainly a case that needs to be looked at. What is the comparative value around this scenario with using pipeline storage when the end use is still electricity? And there's still some value in looking at pipeline infrastructure for that. How do the costs stack up? So there's more work to do to look at that broader question. So in terms of key takeaways coming out of the study that was produced, what was clear to us from what we analysed, that across a wide range of transmission scenarios, the energy transport and storage via pipeline infrastructure is much more cost effective than energy transport via power lines and energy storage in BESS and pumped hydro. Hydrogen pipelines cost more to transport and store energy than natural gas due to design limits and energy density. And to replace compressible gases with zero carbon electricity would lead to a much higher transmission infrastructure cost to deliver that new energy. So it's a really important outcome in terms of energy infrastructure system design. And where gaseous energy is part of the energy value chain, energy transport and storage via pipeline infrastructure is a much more cost competitive option when moving energy over distance and at scale. So distance and scale are important. The longer distance, the larger scale, the more cost effective you're looking at for hydrogen pipeline infrastructure and natural gas infrastructure, obviously. And lastly, reliability differences in terms of losses of supply are an order of magnitude different, favouring pipelines over electrical transmission. So it needs to be part of the discussion around looking at these comparative options. Some final thoughts. Energy systems are complex and multifaceted. So beware of binary assessments in a complex system. And we're seeing a lot of that, certainly sometimes in the political areas of Australia, there's certainly a lot in media. There's a lot of simplistic discussions happening around it's one or the other technology. Really, there's no reason to set policy to select a winner. Investments and policy decisions are more effective if they remain technology and medium agnostic, and they're driven by performance outcomes of cost, reliability, and emissions reduction. So it's really what we want to see more in the debate, certainly in Australia, is a more balanced, agnostic approach to energy, so we get the best value outcome, both for emissions and for value and for reliability. So the energy system overall that achieves our targets through this energy transition, as well as at the end point of net zero, in my view, it will be a system of different technologies acting together as a complementary system. So we're certainly going to be seeing more investments in electrical infrastructure, certainly a large amount of investment in renewable generation that's happening extensively in Australia. And we're going to see hydrogen, in my view, will play a big role in this, and possibly a continuation for some time for natural gas, which provides some reliability through this transition. So it's going to be a complex matrix of energy infrastructure, I think, going forward. Thank you.
Great. Thank you very much, Josh, and thank you, Jordan, for a very interesting presentation. I'd encourage audience to put some questions into the question and answer box. I'll maybe start with a couple of my own, and actually some that are, I think people have already touched on one of them. One of the things we have, I'm interested in your storage and your pipeline storage. Is that the standard way that natural gas is stored in Australia, or do you use salt domes? Do you have salt caverns that you can use in Australia? And is there any interest in using salt caverns for hydrogen storage?
There is some salt caverns around Australia on a couple of the couple of quite remote areas, but in a few different regions. We do have underground gas storage currently, both on East Coast and West Coast in Australia. So that is part of our energy infrastructure. So that they do have a function in how we store energy really seasonally. So underground gas storage in Australia is very much used for seasonal storage, not as much for really short-term storage. We're fortunate, certainly on the East Coast of Australia, our gas pipeline infrastructure is very interconnected. So probably similar to Canada, looking at your map as well. So there's a large amount of storage in this combined infrastructure, and energy is moved up and down the coast as needed to points of use. So we do recognise that in our gas system in Australia, a lot of the short-term energy storage is happening in our gas pipelines. It's not really talked about much, but there is complementary geological storage, and certainly for hydrogen, that is something that's been looked at long-term. Underground gas storage at scale is generally going to be more cost-effective if when you have the need for storage at a specific location. So it's sort of that trade-off. We don't always have the luxury of the right geological environment, the right deposits in the areas where we need storage. So that's sort of, I guess, an ongoing assessment.
I might just add that, the underground gas storage that we do have in Australia, we've typically been using produced hydrocarbon reservoirs. So, for example, we have the Iona underground gas storage facility near Melbourne, which is a large demand centre, and that's essentially a repurposed natural gas reservoir. The CSIRO over here, our national research agency, is investigating the possibility of using those same reservoirs for hydrogen storage, and we look forward to seeing how that turns out.
No, that would be interesting. Maybe, some of your analysis, you looked at different scales. When I think the lowest was 10 terajoules, which is about 71 tons hydrogen a day, right? I'm wondering if you've ever looked at something even smaller. I mean, one of the questions that we're getting a lot of within Alberta is the idea of fueling stations that might be hydrogen fueling stations, sort of 4 tons a day would be a nice size for heavy duty trucks. Bringing, there's a question, it's pretty expensive to truck hydrogen as liquid hydrogen or compressed gas to the fueling station. There's an interest in pipelining. Obviously, if it's a distance short, you can make it work. But versus electricity, and just maybe generating your hydrogen right on site. I was wondering if you looked at, have you ever done any scaling when you go down to an order of magnitude or two lower than what you've reported in this study?
I guess we did as part of the study. There has been a lot of interest in converting some of our major highways in Australia for heavy vehicle hydrogen freight. So there's I guess, public funding announcement at the moment from 2 state governments who have combined to identify Australia's busiest freight route, the Hume Highway, and earmark that to be a hydrogen highway for freight. So looking at setting or developing 4 to 5 different hydrogen refueling facilities along this major highway. the main base of that at the moment isn't looking at pipelines, because they've really gone to the market for fuel retailers to bid this work. Jordan, I think, will have a comment to say, because I think there's probably work that may be conducted soon to look at that very problem.
Yeah, exactly. And I did just want to tell a little bit of a story in that when we were first framing this study, I actually expected to find a crossover point at the low demand end of this study, where power lines became more cost effective than hydrogen pipelines. And when we didn't find that, I kept hassling Josh to go smaller and smaller. But we were building this. We did want to build this the assumptions of this study around transmission infrastructure, and it's a very different set of assumptions to go for distribution infrastructure. So that 10 terajoules a day was about as far as Josh would let me to go, going smaller in scale to keep the same set of assumptions. And we've since been talking with Energy Networks Australia, who are the association that represent gas distribution networks in Australia, as in the smaller to individual households type distribution, to do a similar type of study. That said, so following on from the hydrogen highways concept, whilst the initial government funding programs are looking at individual refueling stations, there was recently a consultation on the National Electric Vehicle Strategy for Australia, in which APGA proposed the possibility of using a pipeline header, essentially based off of the 500 kilometre 10 terajoule per day use case in pipelines versus power lines, to cover two 1,000 kilometre sections of pipeline that just happen to have a really good renewable electricity resource in the middle of those power lines. So whilst it is very much a high level, hey, the pipeline would be pretty low cost transport and storage for any refueling stations who could tie into it along these networks. It doesn't go into the actual cost of refueling because that's not our expertise, but I'll drop a copy of that submission into the chat. So if anyone's interested in where we've taken that idea, feel free to. And we intend on working that idea into a larger body of work that considers hydrogen pipelines around Australia in the coming year.
I'll probably just add, we've got a number of hydrogen hubs across Australia. They're all looking at the hub and spoke model for hydrogen refueling infrastructure. Scale is important for hydrogen, so if you can consolidate your production, it's going to be a lower cost product. Often the hub and spoke model, the different users of hydrogen are not along a linear corridor. So the advantage of a highway is that you've got a linear corridor of use. So I think it's definitely something that's worth looking at because of that reality, because you get consolidated hydrogen production at scale in a single location, which is more cost effective, and you get to take advantage of a linear corridor, which is well suited to pipelines.
So when you look at markets for hydrogen, and that you might be looking at pipeline distribution too, is it primarily the transportation markets, so trucks and trains and buses? Or are you also looking at possible heating markets, industrial heating or space heating? I mean, I would think the climate in Australia is such that you might be better with heat pumps. We tend to have in January in Edmonton, I might say it's 8 times more natural gas demand than in August, right? So, so just the extremities of temperature difference. I don't know, just an interesting that opens up the opportunity for pipelines a lot more, because there's no way you're going to be, it's in a heating application. If you don't have pipelines, you don't have heating. So, Do
you mind if I jump on that, Josh?
Yeah.
So Australia is quite large, as you saw. So we do actually have quite a stretch of climates across Australia, and in particular, a few major cities of Melbourne, Melbourne, Canberra, and say Hobart are reasonable size centres, both economically and population-wise. Historically, Melbourne has been highly reliant on natural gas for heating in the home. The Melbourne gas market moves from about 400 terajoules per day worth of demand in summer to about 1.2 petajoules per day demand in winter. So not quite the eightfold, but getting up there. It's probably on the fringes of where renewable gases start to become economically viable. And actually, I hope to be able to publish in the next couple of days, if not a week, some analysis that's based on pipelines versus power lines, but then considering the entire supply chain down to heating appliances in the home, which demonstrates that there is a cost competitiveness between electrification and renewable gas use in the home for Melbourne freestanding homes that use gas today. So there is, it's not quite, it's not all sunny and warm in Australia all the time, but even in the states where it is nice and sunny and warm, say where I live in Brisbane, which is about 2,000 kilometres north, there's people still using natural gas, despite the fact that it is less cost effective than electricity today. So gas is a fuel of choice as well, and that will flow into things as well. I don't know if it has to be actually cheaper for people want to choose to use a gaseous form of energy.
Probably add, David, like there's been a lot of focus on transport infrastructure at the moment because of the costs. You know, it's a lower hanging fruit for the hydrogen, I guess, value chain. That's less reliant on R&D development and the cost curve coming down than areas like heat or other uses of or industrial process gas. There's certainly going to be, you know, a large proportion of our gas does go to electricity generation, but it also does go to a lot of our industrial heavy industry. That's an area that's going to be incredibly difficult to electrify in any sort of cost competitive way. So gas for the process and heavy industry, certainly looking heavily into hydrogen. You know, we may see a steel industry return to Australia that's looking to leverage that as well. So we you know, have lost some of our steel industry and you know, to China and India and other nations where we export our iron ore, but we're really looking heavily at you know, being a major hydrogen producer, green steel as a market. Do we reinvest in developing our own green steel industry? We have all the ingredients for that. So it's been looked at a range, but the reality is that that's some time away because a bit more reliant on technology innovation and cost curve.
Okay, and I see we're almost out of time. There are some great questions I was hoping to get to, but we've should have been a little more efficient in my questions. I'm sorry. There's some terrific questions there. What I'd ask is, we'd like to pass those to you, and maybe we can help to get the questions through those asking. There's one about ammonia as a possibility. We've done work in that space, and others on transportation efficiency and pipeline materials. I know there's a lot of interest here. Maybe we can get you guys back again to talk about your learnings on pipeline materials and how to repurpose existing natural gas infrastructure for hydrogen. So I'd like to end by thanking you very much for coming to present today and joining us. I know it's early in the morning there, and we really appreciate it here. So thank you so much.
Thanks for the opportunity.
Thanks, David.